Hello students, next we look into the topic of sampling. Sampling is a very important topic because it helps an analog signal to be converted into a digital signal. So all the digital gadgets that you see, all the digital information that you see, its original source must have been an analog signal. And converting from analog to digital, there is a three-step process where the first step is sampling, the second step is quantization, and the third step is coding. Out of which the first step, sampling, is what we are going to deal here. Sampling is shown with a simple diagram here. Suppose if we are going to have a signal x of t, which is drawn like this, it's an analog signal x of t, it is dependent on time t. That signal, we are going to sample it, and we are going to suppose sample it with a frequency, with some frequency which is some 1 by t, where t is the separation between two samples. The separation between two samples is capital T, and the output that we get in such a case is xs of t. Now how do we sample? See, at every time interval of capital T, we are going to close the switch. So this switch is closed at every time interval of t, capital T. So what we will have is not an original signal as it is drawn here, but a sampled version of the signal. So sampling means what? To take a portion out of the original. That is sampling. So here we are taking some portions out of the original signal rather than using the whole signal. Now, when looking at the figure, you might feel that if we are going to sample a signal like this and get an output which is like this, isn't the information lost? Well, it may look like the information is lost because we are losing most of the points in between, or most of the signal in between. But as you will study next in the sampling theorem, if you are going to sample a signal according to what is called as the Nyquist rate, you will be able to get this original signal back from the sampled signal if the rate of sampling is based on Nyquist criteria or the Nyquist rate. So basically it means if you are careful at sampling at a particular rate, you can get this original signal back. Now don't think that, when I am talking about digitization, I am talking sampling, I am talking quantization and coding, then don't think that from this signal, from this coded signal, I will get the original signal x of t back. No, that is not going to happen. So if a signal is converted from from analog to digital form, you cannot reconstruct the original signal, which is x of t, back from the digital signal. You cannot do that. Okay, why? Because of this quantization. Because in quantization we lose information, but in sampling we do not lose information. Let me make that thing very clear. In sampling we never lose information. We can reconstruct the signal, original signal, back from sampled signal. But once the process of quantization is over, the signal component is lost, or some of the information is lost. Even from quantization to coding, there is nothing lost, but because the process from sampling to quantization, there the information is lost. From the digital signal you cannot get the original signal back. But there are lots of advantages of a digital signal. That is why most of the signal are converted from analog to digital form. So next let us look at the sampling theorem. The statement of sampling theorem is: a band limited signal x of t with x of omega. X of omega is basically the frequency component of the signal x of t. So a band limited signal, band limited means the frequency of the signal, the various frequencies that we are having, it is limited to some higher frequency. You are not having a signal, a frequency beyond a certain highest frequency. That is called as a band limited signal. That means its frequency band is limited to certain frequencies. So a band limited signal x of t with x of omega is equal to 0 for frequencies above some maximum frequency omega m, or which can also be said in terms of frequency f as capital X of f is equal to 0 for f greater than or equal to some maximum frequency fm. See, both of these are same statement. The only thing is that omega is 2 pi f. So here I have taken out the 2 pi factor. That is only difference. It means one and the same thing. Okay, a band limited signal x of t with x of omega is equal to 0 for frequencies beyond some maximum frequency can be represented into and uniquely determined from its sample. And uniquely determined means you can find out x of t back from the samples xn of t if the sampling frequency f of s is some frequency greater than the maximum frequency fm that you are having, the fm frequency that you are having, twice of that frequency. So suppose if I am having a band limited signal which has a frequency of a maximum frequency of, let's say, 10 kilohertz, then if you are going to sample it at a frequency twice that means 2 into 10 kilohertz, which is 20 kilohertz. So if you sample the signal with a frequency greater than 20 kilohertz, then you can uniquely determine it, or you can uniquely get that signal x of t back from the sampled signal. Okay, where what is fm? Fm is the highest frequency component present in the signal. Let us look at the proof. So what is basically a sampling process? The sampling process is you take the original signal x of t, you multiply with a train of delta sequence. Now, what is a delta sequence? We all know that a delta sequence is something that looks like this. You are having a delta signal at 0. Okay, you are having a delta signal at t is equal to 0. But what is the meaning of a train of delta sequence? A train of delta sequence is when you are having many delta signals. Okay, when you are having many delta signals, and let me draw the delta signals just for your information. So this is at t is equal to 0. The next is at some capital T, and the next one is at some capital 2t. The next one is at some capital 3t, like that 4t, 5t, 6t, like that it will keep on going. Similarly, in the negative direction you will have at minus t, at minus 2t, like that it will keep on going. So this is a train of delta signal. So this is written as delta t, whereas this one is written as delta t with a subscript of capital T, where capital T basically means the separation between. And how do you write this signal? See, we know that this signal is basically this at t is equal to 0, it is delta t, whereas this signal is originally delta t, but it is shifted back. So I will write it as delta t minus capital T, whereas this one can be written as delta t minus 2t. That means you are shifting this, you are delaying the signal by 2t. Similarly, this can be written as delta t minus 3t. So if you would see, this delta t is basically a combination of delta t of t is basically a combination of many delta signals, which is delta t and delayed version. So delayed version I will write it as minus nt, where basically n is going to go from n is equal to all the way from minus infinity to plus infinity. Okay, this is important that we should remember that when we are talking of a train of delta sequences or delta signals, it is basically this particular equation. Okay, so it's a combination of many individual delta signals delayed in time. So I will write this equation, this part, let me write it as this is equal to summation n is equal to minus infinity to infinity delta t minus nt. So multiplying this signal, if I am going to multiply this signal with any analog signal, let me draw on top of that itself. If suppose there is an analog signal like this, okay, then what is going to be the output? The output of multiplying this sequence of samples with this message signal is that we will get only signals at whenever there is a sample. So I will get a signal like this, I will get a signal like this, I will get a signal like this, here I will get it like this, here I will get a negative one, here I will get a positive one. So if I am going to redraw it, it will look something like this, this one, this, then this, here again this one is going to be a negative, and this one is going to be some positive. So this is going to be the original sampled signal xs of t, where each sample is separated by a distance of t. So I can say that it is basically x at n capital T. And that is basically what we are writing as the process of sampling here. That is what we are writing as the process of sampling here. So this green signal that we are seeing here, this is x of t, and this is delta of t, this whole train of pulse, that is going to be delta t of t, and this is going to be the multiplication output. Okay. So I can write xs of t is basically equal to multiplying x of t with delta t of t. So this is what is going to be the output. Let me draw this small, otherwise people will confuse it with capital X. Okay. So this is what is the multiplication that we are going to have, where delta t of t is basically given by this equation. So what we will first try to find out is, see here, if you look at the statement is all talking about the frequency. So everything has to do with frequency. So first thing what I will do is I will try to take what is the Fourier transform of this sequence. Now this you can see it's a periodic signal, this is a periodic signal, correct? It's a periodic signal, and for periodic signal we don't find out the Fourier transform, but we try to find out the Fourier series. Okay, so if I am going to look at the Fourier series, so therefore I will write therefore Fourier series of delta t small t. And remember from the Fourier series what we have studied, that any signal delta t, which the original equation of which is summation n is equal to minus infinity to infinity delta t minus n capital T, which can be represented in Fourier series as, if you remember the equation of Fourier series, we can represent any signal as summation n is equal to minus infinity to infinity Cn e raised to power j n omega s t. Okay, omega s t, where if you remember omega s is the periodicity, and here the periodicity is basically t, capital T. So omega s will be equal to 2 pi divided by t. Okay, so that is something that we have already studied in Fourier series. So that's why here we have written as omega s, where s represents the sampling one. In previous case you might have not seen s, but here we are writing s because of the sampling issue. Okay, where now here you can get c of n as, so I will write that, where c of n you can find out using the equation 1 by t minus t by 2 to plus t by 2 delta t e raised to power minus jn omega st, which we all know that integrating with respect to dt, and we know that integrating delta function, we will always get the answer as 1. So based on that, this much portion will become 1. So basically I will get the value of c of n as, therefore c of n will come out to be 1 by t. Therefore I can basically write the Fourier transform, or I can represent delta t of t, which is based on this equation. I can represent it as summation n is equal to minus infinity to infinity multiplied with 1 by t. So 1 by t is common. It's the same value. 1 by t is a constant, so I can take that as 1 by t outside, and the remaining portion e raised to power j n omega s t is what remains within the summation. So this is the Fourier series. So this is the Fourier series of delta t t. Now the next thing that we will try to do is we will try to use this. Okay, so next page. Therefore, so let us write what we had already written. Now the signal that we are talking about is the sample signal x s of t, which now we have found out is basically the multiplication of xt with the train of delta signals or sequence, and that if we are going to multiply, then we have to multiply x of t with the Fourier representation of delta t, which we had got it as, so multiplied with 1 by t summation n is equal to minus infinity to infinity e raised to power j n omega s t. Correct? So if I am going to multiply, therefore I can say, therefore xs of t, I will now multiply, so I will take x of t inside. So what I will have is 1 by t summation n is equal to minus infinity to infinity, x of t has gone inside into e raised to power j n omega s t. Now here if I am going to take the Fourier transform of the above equation, taking Fourier transform both sides, so taking, we will write Fourier transform of x s of t is going to be the Fourier transform of whatever is inside in the right hand side, which is 1 by t summation n is equal to minus infinity to infinity x of t dot e raised to power j n omega s t, where the Fourier transform in the right hand side, in the left hand side, will be basically capital X s of omega. Okay, because that is what is the Fourier transform of any signal. The letter becomes capital X s of omega. Okay, and in the right hand side we will take 1 by t outside, and Fourier will be happening for t. The Fourier transform is for t, isn't it? So summation also I will have to take out of it. So what I will have is the Fourier transform of only what is inside the summation, which is x of t. Let me write it properly, x of t into e raised to power j n omega s t. Now we have already seen the frequency shifting property of Fourier transform. So I will write, using the frequency shifting property of Fourier transform, which basically translates as if x of t gives a Fourier transform of x of omega, then multiplying x of t with e raised to power j omega naught t, that means a complex exponential function, will basically shift the frequency plot by the value omega naught. That is what is the frequency shifting property. So if you apply that same property in this above equation, here you can see that x of t is basically multiplied with e raised to power j n omega st. So this n omega st is going to be omega naught when we are going to consider this whole equation Fourier transform. So I will write, therefore I will get xs of omega, which is what we had got on the left hand side, and the right hand side basically I will have 1 by t summation n is equal to minus infinity to infinity. The Fourier transform of x of t is x of omega, then multiplying with this factor will give us minus n omega s. Okay, now this is in omega terms. We know that omega is generally equal to 2 pi f, where 2 pi is just a constant and f is the frequency. So I can write this also as, or x s of f will be equal to 1 by t summation n is equal to minus infinity to infinity capital X, and here instead of omega I will write f minus, and n omega can be written as 2 pi divided by capital T. Okay, where the 2 pi factor will go, and I will get 1 by t, where 1 by t can be written as fs. So I will write this as nfs, where fs is equal to 1 by t. Let me write this properly, fs. So which is the sampling frequency. Okay, so now if we are going to look into this particular equation, so what does it say? It says that the Fourier transform of the sampled signal will be based on this equation. Okay, now if suppose I am having a signal, let's say some signal like this, whose Fourier transform if I am trying to take, then I will get with respect to f, if suppose I am going to get some frequency plot, which let me draw something like this. I should draw it in such a way that it is a mirror image, so I will draw it like this. Okay, so suppose this is the frequency plot and we are having some maximum frequency fm beyond which the frequency is 0. Okay, so this is the original x of t and this is x of f. Then the sampled version of the signal, sample version will be basically multiplied whatever we have done here. So it is basically going to be the sample version of this signal. So if I am going to take the sample version of this signal, which is xs of t, and we have seen that the Fourier transform of xs of t is basically going to be, we just now saw, it's going to be xs of f, where xs of f is basically given by this equation, which is what? Which is, let me now draw this very carefully, which is, so if I am going to draw this signal, I will have this signal basically drawn like this, okay, which is x of f. Now what is this equation? See, this equation is a series of different x of f shifted by this value. Okay, so suppose if n is equal to 0, in this case, suppose if n is equal to 0, then I will get here as x of f only, isn't it? Whereas if it is n is equal to 1, if I am going to take n is equal to 1, I will get x of f minus fs. If I am going to take n is equal to minus 1, then I will get in this side x of f plus fs. Then similarly next, if I am going to take n is equal to 2, I will get x of f minus 2fs. So like that, I am going to have not just a single x of f, but multiple copies of x of s. And all of them are not lying in the same spectrum, they are shifted in frequency. Some are shifted by fs, some are shifted by 2fs, 3fs, like that all the way up to infinity. So what I am going to have is, I am going to have, when I am going to write this equation, in this equation I am going to have multiple copies of the same frequency spectrum shifted by fs minus fs, similarly 2fs, 3fs, like that I will have to keep on drawing. Let me draw that diagram more clearly for explanation purpose. So suppose if the original signal has a frequency spectrum like this, okay, where the frequency spectrum is extending from minus fm to plus fm. This much is the bandwidth of the original signal, and generally 0 to fm we will say. Okay, so this is x of f, but when we sample it, we are not going to just get one spectrum, but we are going to get a series of spectrum, all having similar shape, which is x of f, but they are all shifted in frequency axis. So let me draw that like this. So now we will say that now this is the spectrum for x s of f, the equation that we have written here, wherein the original spectrum, the triangular spectrum that we have seen, we have now drawn multiple copies, where based on the value of nfs, n means n will be from 0, so this is for n is equal to 0, this will be for n is equal to 1, so this is going to be fs, this is going to be 2fs, this is going to be minus fs, this is going to be minus 2fs, and like that it will go in all these directions. Okay, so this is what is basically this equation going to be. Obviously what has happened here is that the original amplitude, if it was 1, now here the amplitude has become 1 by t. So I will write this original amplitude of the spectrum as 1 by t. That is something that we have to take care. Okay, so the original spectrum xs of f would have been just this single triangle in between with a height of 1, but now when we sample that signal, the spectrum has turned into this shape, wherein we are having multiple replicas of the original spectrum, all shifted to fs, 2fs, 3fs, like that it is going all the way up to infinity. All the way up to infinity is going. Okay, now based on this fs, you can have the spectrum either coming closer to each other or shifting away from each other. Now suppose if I am trying to reduce the value of fs, that means if I am trying to reduce the value of fs means I have to increase the value of timing t. So if increasing the time value of t means what? Suppose if I am trying taking a sampling wherein I am going to switch off the switch on the switch that we are having for switching. Suppose I switch it at this rate, tick 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 tick, like that in this time period, then I am having a certain frequency of sampling. Suppose if I am going to have a sampling frequency, a timing which looks like tick 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 tick, you can see that it is more fast. If it is more fast means I have reduced the time gap capital T. But if I am going to increase the value of capital T means I am going to switch off, or I am going to switch on the switch every time at tick 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 tick. So you can see that the time period when I am going to switch off the switch every time, switch on switch off, that is going to basically change, and if it is the time period is going to increase, the value of fs will decrease. So if I am going to reduce the value of fs, what we will see that this spectrum will basically come closer. So let me draw that. Now in this second situation that we are having, suppose we select f of s such that the two ends of the closely lying spectrum touch each other, just touch each other. Okay, so this is at minus fs, this is at minus 2fs, sorry, minus 2fs, then you can see that what has happened is that we have reduced this distance between two closely lying spectrum. And how do we reduce that? By basically reducing the value of fs. So if I am going to reduce the value of fs, this distance between two closely lying spectrum, that is basically going to change. And how do I reduce the value of fs? By increasing the value of t. By not increasing the value of t, by increasing the value of t. So if I am having a reduced rate of sampling, like just with previous case I have said, if the sampling is like take, instead of that, if I am going to delay this, like take, you can see that the spacing has increased, isn't it? So if I am going to increase the spacing, the value of fs is going to go down, and that means the spectrum is now going to be close to each other. Now one thing that we must remember is that the height is going to be 1 by t of the spectrum. The height is going to be 1 by t, which is as we have drawn here, we have given in this equation. So that is not going to change. Now there is another condition. If I am going to further reduce the value of fs by increasing the distance of t, if I am again going to increase the time length of t, then the value of fs will again go down, and you will have a situation where the spectrum tends to overlap. Okay, so when they overlap, what happens is that, see here you can see that the two triangles are overlapping each other, isn't it? This overlapping is called as aliasing. In certain textbook, the spelling is all the same. It is called as sometimes it is called as aliasing, sometimes it is called as aliasing. Okay, so the aliasing basically happens when you are having such a situation. So I will write, so this situation, when it happens, what has happened is that the original spectrum has got corrupted. Now why do I say that? See, if I am going to have a low pass filter from which I can extract this central portion, then I will get the original signal back, because basically low pass filter does what? It basically totally negates the other spectrum. It will take only the central spectrum, and if I get the central spectrum back, it means that I have got the original signal back. That can even happen here, that can even happen here. I can draw something like this. If I am going to put a low pass filter, I will get the original signal back. But what about here? If I am going to put a low pass filter, will I get the original signal back? I will not get the original signal back, because the signal is already corrupted by the closely lying next spectrum, and that is basically called as the aliasing error. So if you don't want this aliasing error to happen, you have to take care that the sampling frequency fs is not so much small that these two spectrum will overlap each other, and that will happen at least if you maintain this. And what is this condition says? This condition says that at least fs should be equal to how much? From here it is 0 to fm, from here to here again it will be another fm, because this belongs to the triangle. So we know that this width of the triangle is how much? Fm. So here also it will be fm. So basically combining this whole length, we will have 0 to fm and then another fm, so we will have 2 fm. So minimum, at least we should have fs is equal to fm, twice fm, sorry. Fs, let me write it properly. Fs should be equal to twice fm. Then we may be able to, theoretically we may be able to reconstruct the signal back, because you can put a filter. But again, if I am going to draw the filter will look something like this, isn't it? The filter will look something like this, the spectrum of the filter, low pass filter. But we know that such a filter is very idealistic filter, because in an ideal filter only you can have this shape. And we know that generally the shape of a filter, basically if I'm going to draw it, the spectrum, it will basically look like this. So it's not going to be an ideal case. It's very difficult to draw an ideal filter like this. It's very difficult to design an ideal filter like this. So, minimum at least this much should be maintained. Or if you are having a non-ideal filter, if I'm going to draw again a low pass filter, suppose if I'm going to have a low pass filter which looks like this, and you can see that this is not very ideal filter. In this case, it is easily taken out. So I can say that in this particular situation where Fs is greater than twice Fm. Why greater than twice Fm? You can see that this width is twice, this width is Fm, this width is Fm. From here to here it is Fm, from here to here it is another Fm. So this is greater than 2 Fm. So in that case we are having the signal recovered. Even in this case the signal can be recovered if we are using ideal filter, but in this case wherein the value of Fs is less than twice Fm, we are not going to get the signal. Instead we are going to have a signal which is having an error which is called as the aliasing error, and from there is where we get the the statement wherein we had said that in the statement that if the sampling frequency is this, that is Fs is greater than or equal to twice Fm, in that case we will be able to recover the signal back. Okay, so the sampling theorem, hence we can prove it like this. So thus we can say that for a signal x of t to be recovered from its sample, we need to satisfy two conditions. The first condition is that x of t should be band limited. X of t should be band limited. That means it should have some maximum frequency beyond which the frequency components are 0. Okay, so it should be band limited to some frequency, to some maximum frequency, to maximum frequency Fm, some maximum frequency Fm. That is the first condition. And the second condition that we have to take care is that we should sample it. The sampling frequency should be the sampling frequency which is written as f of s should be greater than or equal to twice Fm. Should be greater than or equal to twice Fm. These are the two conditions that we need to satisfy. Another thing that I should say is, this width, this particular limitation wherein we have this gap is called as guard band. This is called as guard band. That means there is a band which is acting as a guard between two frequency spectrums so that they are not overlapping. Okay, so this will occur where? This will occur in this particular condition. So there will be a guard band in this particular situation. Okay, and we have to take care that there is a guard band because the filter is not ideal. So if the filter is not ideal, we have to generally follow that Fs is greater than 2Fm and not keep it equal to 2Fm. That's why the frequency rate is always, the sampling rate is always kept more than twice Fm. For example, the human voice, the limit of human voice, the human voice basically ranges, if you don't remember, it ranges basically from 300 Hertz to 3 kilohertz. Okay, so beyond that it does not go, 3.1. Okay, so if I am suppose taking that the maximum frequency is 3 kilohertz, in that case I can sample with a sampling frequency which is twice that is 6 kilohertz, isn't it? But 6 kilohertz is going to leave no guard band. So I will mainly, let's say I will sample it with 7 kilohertz or maybe even 8 kilohertz. Generally we will say that it is 8 kilohertz. So the human voice can be sampled at 8 kilohertz and still be recovered from that particular signal. So based on this, we will have two terminologies. One is called as the Nyquist rate. Okay. So the Nyquist rate is the minimum sampling rate at which a signal can be recovered from its sample, and that minimum rate is twice FM. So I will write that the Nyquist rate is equal to twice FM. Okay, so this is the Nyquist rate. See, here I have not put greater than or equal to, I have used equal to because I am talking about the minimum sampling rate, isn't it? The minimum, at least you have to keep twice FM. That is basically the Nyquist rate. Similarly, we have what is called as Nyquist interval, where Nyquist interval can come from Nyquist rate itself. Let me name the Nyquist rate. Nyquist rate is sometimes called as, it is called as Fn. So Fn should be equal to 2 Fm, where Fm is basically the maximum frequency. And Nyquist interval is basically just the opposite of Nyquist rate, no, not opposite, it's the reciprocal of Nyquist rate. That means I am talking about Nyquist interval. Nyquist interval, it is just in terms of time. Nyquist interval is 1 by Fn. Okay, 1 by Fm, which is equal to 1 by 2 Fm. Generally it's not asked. Nyquist rate, instead of Nyquist interval, it is mostly Nyquist rate that is generally asked. Now we have to also mention what are the problems of not following the sampling theorem properly. For that we have to remember that if you are sampling, so I will write here, let me write it as a separate point. If your sampling rate is greater than, or not, I will start with equal to. Okay, if it is equal to twice Fm, then I will call it as sampling at Nyquist rate. Okay, sampling at Nyquist rate. Why I am telling these terms is because whenever you read materials, you will come across it. So when we say sampling at Nyquist rate, it means we are sampling at 2 FM frequency. If Fs is going to be greater than 2 FM, then I say that the signal is getting oversampled. And oversampling is good because it makes the design of low pass filter for recovery of the signal easy. So oversampling is in a way good. Then we are having what is the problematic case, which is if Fs is less than 2 FM, then what we have is undersampling, which leads to what is called as aliasing, which leads to aliasing. Okay, in certain books it is even written as, it is also pronounced as aliasing. Certain people call it as aliasing. It does not matter. You can use whichever form you want to use. Okay, so what is the reason for, what is the main reason for aliasing to occur? So aliasing can occur if the signal is not band limited, meaning it does not have a, it does not have a maximum frequency. So generally what happens, if suppose you are having a spectrum like this, you may have a spectrum like this which does not ends abruptly. It basically have some frequency which it's going on, it's having a small frequency components, then generally what people do is they basically take a filter and they cut off this much part, and they forcefully band limit it. They forcefully band limit it to some maximum frequency. That kind of filter is called as an anti-aliasing filter. Okay, anti-aliasing filter, which basically makes it a band limited signal. That is the first thing that they do. Okay, you can write it that x of t is not band limited. That is one of the reasons how aliasing can occur. The second reason why aliasing can occur is if f of s is less than 2fm. So these are the two, these are the two reasons why aliasing can occur. And to avoid aliasing, we can write next and the last part. To avoid aliasing, the first thing that we will do is use anti-aliasing filter. Use anti-aliasing filter, and what does that do? To trim the bandwidth, at some frequency fm, some maximum frequency fm. So that is what the anti-aliasing filter does. There is a cutoff frequency of the anti-aliasing filter. Beyond that, whatever frequency component is there in the signal, it will basically trim it off. Okay. Second is sample it at fs should be greater than the Nyquist rate or 2fm. It should be greater than the Nyquist rate or 2fm. So this thing we have to take care. Now when I am saying anti-aliasing filter, see, even inside our phone there is an anti-aliasing filter, okay, which basically takes the sound and trims off the extra frequency that are there beyond a certain frequency. Let's say 3 kilohertz. Beyond 3 kilohertz it will just trim it off, okay, and then the remaining signal is transferred. So that is why the reason in certain phone calls you are not able to recognize some of the voice of the people, because certain frequency components in their voice are trimmed off, they are cut off using the anti-aliasing filter, so that there is no aliasing occurring. Okay, with this we will finish the theoretical part, the proof of sampling theorem for a low pass signal. Thank you.